Yeah.
So we're going to use the 4-point probe to put it into operation, turn on the power, let it settle. Then we're going to switch to ohms, and it's a Kelvin measurement where we have two outer contacts for which the current comes in and out, and then we have two inner contacts that measure the voltage. That way it gets rid of all the error due to the wires. All right. There's more to it on that. So then we want to press auto scale and then filter. And it's blinking. So we don't have anything on there yet, which is why it's overflow. It's trying to push current and the voltage is going towards infinity. All right. So this is the 4-point probe setup, and we have a certain way of measuring things. It might be hard to see, but there's 4 probes that will come down on the wafer. The outer probes pass the current, the middle probes measure the voltage. And it tells us the sheet resistivity, which I don't have a lot of time to go over, but by measuring the sheet resistivity, I can determine the resistance of any lines that I make, but also it's a proxy for thickness. So if I wanted to measure the thickness of this aluminum wafer, I could measure the sheet resistivity if I had the calibrated material parameters. It's non-invasive and it's really quick. So what you'll all do is you'll start with aluminum, and this is about 1,000 angstroms on silicon dioxide. And we're going to measure 1, 2, 3, 4, 5 places. The flat is down, and that's how we do it in this lab. So I just place it here. Okay, actually, I place it in the center, and then I just move this stage, and it's roughly in position 1. Comes down, 0.01, or 19.7 milliohms. You have to scale that by 4 and a bit to get the sheet resistivity. Then you take position 2. All right, 0.02. And so these are typical values, right, that you know that if you're getting this, it's working. 0.022, right? 0.019. And then we would have the final one. All right. Now, yeah, different people will measure slightly different areas, but we can certainly do a quick wafer method. Now this wafer has been diffused N plus into P, and so it's actually a solar cell, it's actually a diode, it's actually could be source and drains. Measuring the resistivity of that is important as well. And we should get different values again. Position 1, 0.36, right? Position 2, 0.7. And so actually a class activity is everybody measures this, gives each other the data, and see what the variance is per operator measurement. 7. So I could be user 1. And so this was processed in a diffusion furnace over there in our solar cell class. Okay. There's more of these wafers in the back there. I think this one should break. Now that's great. We showed 2 things that were working. What about when it doesn't work? Well, this is a wafer that's got silicon dioxide on it. It's an insulator. We really shouldn't be able to measure the resistance. I'm just going to put it in the center. Really, finding out that it overflows in 5 positions isn't necessarily useful. All right, overflow. It means it can't measure. There is a finite number, it's not infinite, but we can't measure it. And then this is what you would call an undoped wafer. Now silicon is never truly undoped. It can be very lowly doped, but you will get a number, but you'll see it bounce around quite a bit. So I'm just going to put it in the middle, and it's 9K, 13, and it's still, the filter's still blinking, So it hasn't really found its average. And I suspect that light is playing an effect because it's so undoped. So it's not really giving me, let's say, a useful number, except to tell me that it's undoped, if I should have forgotten. Right now I have undergraduates doing research on finding the reliability of this system, but this is something we use in EE129, EE165, and the new NE189. Enjoy.